Okay, we're going to look at a couple more limit problems where x is growing without bound. X is approaching infinity. And so I have here two examples that are rational functions. So I have a polynomial over a polynomial. So I have x lots of places in both of these functions. So thinking about what happens as x approaches infinity, we could maybe think about the individual pieces and think about if we can reason together what the overall function would do. But there's actually another strategy that is helpful for these. Part of why just looking at the individual pieces maybe doesn't work so well in a problem like this is that you've just got x so many different places. Also, you might notice on both of these, like in some of the last examples we looked at, as x approaches infinity, both the numerator and the denominator grow in size without bound. So both of these, the numerator would get infinitely large but negative, and the denominator would get infinitely large. So both of these would have a numerator approaching negative infinity and a denominator approaching positive infinity. But these two problems have very different answers. So we're going to talk about how to reason through what those answers are. So we looked at a problem in the last video where we started with a rational expression. We had only one term in the denominator. And my suggestion for that was to split it into two fractions, and then you could look at the individual pieces a little bit easier. That doesn't work here because you have more than one term in the denominator. You can split up a numerator. If I had only one term in the denominator, if I didn't have this 2x and I had only 17x squared, I could split that up over 17x squared, but you can't split up the denominator like that. Adding fractions doesn't work like that. There is an algebra trick you can do, though, which is helpful. And so I want to just talk through that and show you that. This is not an algebra trick that I would have thought of if somebody hadn't showed me that it would work. And I would say probably that's the same for you. If somebody hasn't showed you that this works, it's not an obvious thing to do. Because at first, it seems like you're making these problems more complicated. But then what happens eventually is you get some simplification and you're able to think about those limits. All right, so for both of these problems, I'm going to use the same strategy, but we have very different limits on both of these. I'm going to start by multiplying both of these rational functions on the numerator and denominator by 1 over x to a power, where that power is the highest power of x in the denominator. So for both of these, I'm going to start by multiplying by 1 over x squared on the numerator and 1 over x squared on the denominator. So you're just multiplying by a form of 1 here, so you're not changing the value of the overall function. And it looks like you're making things much worse because you end up with fractions inside fractions, which starts to look awful. So that's why this is maybe not something you would think about doing to start with. But when you do that, you get some nice simplifications. So I'm going to go ahead and do that, and then we'll look at the simplifications. Notice I'm writing this limit out front of every step here. So it's here until I actually evaluate the limit at the end. All right, so on the numerator, when I multiply through by 1 over x squared, my first term on the numerator there will just be 1 over x squared. But the second term on the numerator, when I multiply 3x squared times 1 over x squared, the x squareds will cancel. And so I'll be left with minus 3. All right, so maybe that helps, and maybe it doesn't. Let's see what happens here on the denominator. When I multiply by 1 over x squared, 17x squared, the x squareds will cancel, so I'll end up with 17. And then on this second fraction here, 2x times 1 over x squared, one of the x's will cancel. And so I'll be left with plus 2 over x. So one thing you might notice is the function I started with had x in 3 places. I did this, so now I got less x's here, so that's helping a little bit. I also have only one x in the numerator and only one x in the denominator, so that's pretty good. The other thing that you might notice too is these, I got a lot of constants in here, but these two parts that I circled, it's relatively easy to think about what happens to those two things as x approaches infinity. As x grows without bound, approaches infinity, the denominator is going to keep growing and growing and growing, larger and larger and larger positive. The value of this fraction, 1 over a very large number, will approach 0. And this fraction also will approach 0. The numerator will be 2. The denominator is just going to blow up, get larger and larger and larger, so the value of that fraction will approach 0. This stuff that I wrote here is really scratch work, but that's what I would think about when I'm thinking about evaluating this limit. And so from there, though, I can go ahead and say, well, this part approaches 0, so equals 0 minus 3, and then on the denominator over 17 plus 0. And notice I don't need to write the lim out front here because this is really the value of that limit. So I wrote it in front of the steps where I was just doing algebra. Now I'm just going to simplify this, and negative 3/17 is the answer for that limit problem. All right, so this second one looks a lot like the first one. We talked about that the numerator and denominator both approach negative infinity on the top and positive infinity on the bottom. So both of these problems are similar to start with. Both of them I can use the same algebra trick of multiplying through by 1 over x to the p, where p is the highest power of x in the denominator. So you're going to multiply through by 1 over x squared. All right, so when you do that, I'm still going to write lim, x approaches infinity up front. I'll end up with 1 over x squared. Here, I'll end up with minus 3 over x on the numerator. On the denominator, I'll have 17 plus 2 over x. And then similar to that last problem, all of these little fractions within the larger fraction here, can think about each of those. On all of those, the numerator is constant, the denominator is getting larger and larger and larger without bound. So all of these things that I circled here approach 0. So I end up with 0 minus 0 over 17 plus 0. So 0 over 17 is 0. Okay, so notice both of these problems at the beginning, the numerator approaching negative infinity, the denominator approaching positive infinity. But notice the difference in the answers here. Both of these have answers that are numbers. Negative 3/17 is actually very close to 0, but is not the same as 0. So this is a problem that would be very difficult to do numerically and get this answer numerically. If you plug numbers in a table into your calculator, it would be very difficult to realize that this is the actual value that this function is actually approaching. So these algebraic techniques are kind of helpful, especially for problems where it's not necessarily obvious what's going on when you think about it numerically. I want to just do one other slightly different example that's similar. I'm going to change the power on the numerator to x cubed and leave everything else the same. Okay, so the limit as x approaches infinity, 1 minus 3x cubed over 17x squared plus 2x. So again, I'm going to multiply through by 1 over x squared. You're using the powers on the denominator, the highest power on the denominator, to decide what to multiply through by. We will end up with 1 over x squared minus 3x over 17 plus 2 over x. Okay, so this time I have this x left in the numerator, so this is a little bit different. These two things that I circled will both be approaching 0. As x approaches infinity, 1 over x squared and 2 over x will both be approaching 0. But I also have an x left in this other part here. So I need to think about what that is approaching as x approaches infinity. As x approaches infinity, this is going to grow larger and larger in size. That part will be approaching positive infinity. There is a subtraction sign here I need to be aware of. But when I think about the overall pieces of this and think about putting that all together, on the numerator I have something approaching 0 minus something growing in size. So that'll approach negative infinity on the numerator. And then 17 plus 0, the denominator will approach 17. So negative infinity over 17. So even when I have a very large number, large in size, and divide it by 17, I still end up with a very large number, large in size, but negative, so negative infinity. So all three of these problems here had numerators that approach negative infinity, denominators that approach positive infinity, but we ended up with three very different types of answers to these problems. So this is a good strategy. It doesn't work on every problem. There are other ways to think about these problems. So as long as you're able to reason your way through it and justify your answer, there are other ways to get these answers. But this is a handy trick to use for these types of rational functions. Really works only for rational functions.